Okay, we're looking at collisions in one dimension. So there's two types of collisions. There's elastic collisions and there's inelastic collisions. So to kind of visualize what they are, inelastic collisions occur when basically energy is not conserved. So this is pretty much the vast majority of collisions right here, inelastic. So think of anything colliding. If we compare the energy before and energy after, it's not the same. So what does it mean to not be the same? If you kind of visualize like in a car crash, for example, during a car crash, like two cars collide with each other, and afterwards, the two cars have significant damage. Right, so like maybe like the whole front is crumpled inwards for one. Seems the other, the whole front is crumpled in. So basically, what I kind of think what happened. First of all, when it collides, there's sound. Right, there's sound that occurred. Right, there's heat. When things collide, there's heat. Things heat up. Right? Energy is required to change the shape of something. So basically, originally there was energy, but some of that energy is being like originally it's kinetic energy, say. Some of that energy is being transformed into sound energy. Some is into heat. It's other types of energy, and there's still going to be some kinetic energy afterwards, because after you collide, the objects still keep moving. So that's an inelastic collision. We have kinetic energy. Things collide. Energy is lost. The thing is still moving, so it has kinetic energy, but not as much as before. And elastic collision is like a very idealized scenario when energy is conserved. Probably the closest you can get to thinking of true elastic collisions probably in the subatomic level. Think about how like two objects, like two, I guess, electrons flying through space, and or just subatomic particles colliding off each other. For our macroscopic world, probably one of the closest things we get to an elastic, well, seeing an elastic collision would be two billiard balls, for example, because when two billiard balls they collide, and definitely there's energy being lost because you hear that loud smack when they collide. But because they're so hard, there's minimal deformation and energy. Don't lose too much energy from that. So let's look at solving some of these problems. So this one we have a glider A, and it's moving along what we call an air track. So in my regular science classes, I have one of these things, and it basically allows one or more objects to move on a nearly frictionless surface. Again, we can never get 100% frictionless. There's always going to be some loss of energy, but we do the best we can. So on this frictionless surface, we can have things move, they can collide, and we can observe what's going to happen. To try to simulate an elastic collision, what we would do is we'd usually attach two magnets on each other. So by the two objects actually physically touching, they actually conserve energy a lot better than if they were to actually bump into each other. And whenever you hear sound, you can assume energy is lost. So let's scroll down and solve this one. So we have glider A, and it has some mass traveling some velocity. So usually how we approach these ones, it's called as A and B. I like to set up a little T-chart, because I know that the momentum before must equal to the momentum after. Momentum is conserved for collision in a closed system. So I have some mass A times some velocity A plus some mass B times some velocity B. And later on, I still have those two objects, A and B. So I still have that mass A, but it's traveling at some new velocity, VA prime. I still have mass B, and it's traveling at some new velocity, VB prime. So let's plug in our values. We have 0.450 kilograms, and its velocity is 0.120 meters per second. And we have a mass of 0.700 kilograms and a velocity of 0.05 meters per second. Afterwards, the mass hasn't changed, but now it's traveling in the same direction with a velocity of 0.030 meters per second. And we now have that other mass, 0.700 kilograms. And we're looking for this final velocity of b. Just plug that in. 0.45 times 0.12 plus 0.7 times 0.05 minus 0.45 times 0.03 divided by 0.7. And we have VB prime to 0.010786 meters per second. I can round that to 0.011. Okay, I'm going to store that number. So 0.0107856 or 867143. I'm going to store that number in my calculator so that I have it for later, because I'm going to continue this question right here. So in this question, what is the total kinetic energy before and immediately after collision? So basically, if we find out that the energy before is equal to the energy later on, then we know it is going to be an elastic collision. If it's different, well, if the after is less than, then we know it's going to be an inelastic collision. If the two objects stuck together, we know it's a completely inelastic. So we know it's not completely inelastic because the two objects do not stick together. So basically, I just need to calculate energy before, and that's equal to 1/2 MAVA squared plus 1/2 MBVB squared. So let's see what our values were. The mass was 0.45. Our initial velocity was, what was it? Our initial velocity was 0.12. Okay, initial velocity was 0.12. I'm going to square that. And the other one is 0.7 times initial velocity of 0.05. And I can divide that by 2. So we get an energy of about 0.0041 joules. So I can do the same thing, find the energy after. So 0.45, our velocity is 0.03 squared. And I'm going to use the velocity we just found, that 0.10. So what was our velocity? Okay, sorry, let me plug that in again. Plugged it in wrong. So we have 0.45 times 0.03, sorry, 0.03 squared plus 0.7 times 0.107857 squared by 2. So clearly I actually made a slight error on the initial values I chose, but I intended for this one to be the same. It's impossible to have more energy later on than afterwards. So I intended for these to be the same and to get elastic. But we get the idea. Clearly I should go back and change one of those velocity numbers above. Hopefully you get the idea. If we can calculate the energy before and calculate after and compare them, we can determine if it's elastic or inelastic. Clearly there's something wrong with that number, though, because we cannot have spontaneously gained any energy.